Today we want to talk about friction. Friction is a force that opposes motion. Typically, it's a sliding force. And a lot of times that has to do with the type of surfaces that we encounter when we're trying to push things along. You might know that it's easier to push a laundry basket across a smooth tile floor than it is to push it across the carpeting or across concrete. And yet the basket didn't change, so what's going on? Well, in physics, we want to talk about friction we can't talk about it without talking about these things called proportionality constants. A proportionality constant is simply a number that gives us an idea about how much, in this case, friction there's going to be. The larger this number, typically the more friction we will encounter. The more these surfaces are going to interact with each other. So we have these two friction coefficients. They're given by the Greek letter mu. Mu, like a kitty. Mu looks like an upside down H, or the symbol for micro, like micrometers or micrograms. And then it has a subscript. Mu subscript S is the coefficient of static friction, and mu subscript K is the coefficient of kinetic friction. Static friction is the friction that exists between objects that are not moving with each other. For example, the friction that exists between me and the wall. If I push on the wall and it doesn't go anywhere, there's static friction. And I can increase this force by pushing harder, and there's more friction. And I know that there's more because the wall still isn't moving, which means our forces are still equal and opposite. But kinetic friction is the force between objects that are in motion with each other. You might notice it's always harder to start something moving than it is to keep something moving. Well, when we talk about objects that are in motion or objects that are at rest, we would know that there is a certain amount of friction required to actually get something to start moving. So if you were trying to help a friend move a piano, you would push on the piano, but maybe it doesn't move. Well, if it's not moving, it's still in equilibrium. So if we drew a free body diagram for your piano, of course you would have gravity pulling the piano down, and you would have the floor holding the piano up. And then if you push on the piano, we would have an applied force, Fa. But if the piano doesn't move, this tells us that there is a friction force acting against it, Ff. And if this is not in motion, then it's in equilibrium, and therefore we know that the left forces and the right forces are equal to each other. The up forces and the down forces are equal to each other. So if you're trying to help somebody move something, then you're going to have to push with the maximum amount of force to eventually break it from this state of rest and turn it till it just begins to move. That's the maximum amount of static friction that you can get. After that, once it starts moving, now this friction force changes and it becomes kinetic friction. So because of the irregularities in the surfaces when things are pushed together, we experience this friction force. So when we try to calculate how much friction there is, we have to consider two things. We have to consider what type of materials are interacting with each other. That's where that proportionality constant comes together. We call it the friction coefficient. That's mu. And then the other thing we have to consider is how heavy is the object. So our friction force is then calculated using mu. We would say the friction force, Ff, is mu s times F normal. Remember, F normal in this case is going to be the weight of the object, mg. If we wanted to find how much friction there is and we finally got our piano moving, this friction force doesn't change very much. The coefficient is what changes. If this is in motion at constant velocity, we would know our applied force is still equal to our friction force, but this time now we have kinetic friction. This is, Ff is mu subscript K times F normal. And this is for our kinetic friction. So we're not going to notice much difference. It's still going to be the weight of the object times the coefficient. The weight of the object times the coefficient. The big difference is that mu s will always be a slightly bigger number than mu k. These mu values for friction forces are usually a number between 0 and 1. So you're talking about some sort of a decimal, 0.12, 0.34, something like that. The other thing that's really important is we talked about this being the weight of the object. If we had an object that we began to push up a hill, our normal force is always perpendicular to the surface. This normal force is going to continue to change because if you push something up a hill, you're not necessarily pushing all of the weight of the object. The force of gravity gets distributed, some along the hill and some perpendicular to the hill. So we have to consider that as well. Let's take a look at a problem. Suppose a boy exerts a 36 Newton horizontal force pulling a sled, a 52 Newton sled. That's the weight of the sled. He's going to pull it across the sidewalk, a cement sidewalk at constant speed. And they want to know what is the coefficient of kinetic friction between the sidewalk and the metal sled runners. And they say ignore air resistance. So the first thing that we want to do is we want to consider what type of motion we have. If we're pulling something horizontally, then there are several forces that are acting. This is very different than if we have something that's just acting vertically. So we want to first start off by drawing a free body diagram. So we're going to say, okay, here is our sled. It is simply a dot. Then we want to identify the forces that are acting on the sled. Well, certainly we know that the gravity force is pulling it down. So we know it has a force due to gravity. And they tell us that this is a 52 Newton sled. That's the weight of the sled. Therefore, this is 52 Newtons. And it's negative because it's down. But we have to also assume that the sidewalk is holding it up. So there would be a normal force that is equal to the vertical weight force of a positive 52 Newtons. Now, we can deal with the horizontal forces. Our boy is pulling the sled across the sidewalk and applying a force of 36 Newtons. So this is our applied force. Fa is 36 Newtons. And then we know that there's some friction. But how much? Well, it's in motion. So is there a clue that we can take from the terms in the problem? Well, it turns out that yes. Because they said that the boy is moving the sled at constant velocity, we know that the sled is not accelerating. If it's not accelerating, then left forces have to equal right forces, and up forces have to equal down forces. This tells us that the friction force is negative 36 Newtons, equal and opposite. So they would like to ask us to find the coefficient of kinetic friction. How do we go about doing that? Well, we know that the coefficient of kinetic friction is mu subscript k. And if the friction force, Ff, is mu k times F normal, and we're trying to solve for mu k. Therefore, we rearrange our equation, we get mu k is friction force divided by normal force. Now, truly, this cannot be a negative number, so it's absolute value of the friction force divided by the normal force. If we then plug in our friction force of 36 Newtons, mu k is 36 Newtons divided by 52 Newtons. At this point, we have Newtons over Newtons, and this will cancel, which is good because our proportionality constant does not have a unit with it. If we do this math, we get mu to be 0.69. Mu k is 0.69. That's a fairly high coefficient of friction, but if you think about running metal sled runners over concrete, that's a lot of sticking together, a lot of interaction. That's going to be a lot of friction. So now suppose the same sled, this 52 Newton sled, is going to run on packed snow. And they give us the coefficient of friction. They say the coefficient of friction this time is only 0.12. if a person weighing 652 newtons sits on the sled, what force is needed to pull the sled across the snow at constant velocity? So we're looking for now the applied force. So once again, we want to do the same thing. First, we want to draw our free body diagram. So we draw the sled. Then we want to add the forces that we know about. Well, we know that this sled is being pulled down by the force of the Earth's gravity. Do we know what this is? Well, the sled's weight was 52 newtons, but we have a boy that weighs 650 newtons sitting on the sled. So we consider the boy and the sled one system. We want to look at, well, how much is being pulled downward anyway. So this would be the total of 52 newtons plus 650 newtons. Now the sled is going to be held up by the concrete, so that will be the normal force, which has to be the same. So this is 702 newtons, and this is a negative 702 newtons. All right, now they want to ask us, what is the applied force, Fa? This is what we're trying to find. What we know from the problem is that the sled is being pulled at constant velocity. So when you pull something at constant velocity, we know the net force horizontally has to still be 0. Well, that means there must be friction over here, Ff, and we remember that we can calculate the friction force. Ff is mu k times F normal. Well, in this case, they gave us mu k. They said the coefficient of friction is 0.12. So we're going to plug that in, 0.12 times the normal force. Our normal force is 702 newtons. Okay, so if we plug in 702 newtons times 0.12, we get a friction force of 84 newtons. That friction force is acting over against the sled, so we would make our friction force negative 84 newtons. And we're looking for the applied force. Well, if there's 84 newtons of friction, there must also be 84 newtons of applied force to move the sled across the snow at a constant speed. So Fa is 84 newtons. Another thing that friction does for us is when something is moving through the air, that friction opposes the motion and tends to slow the object down. This friction is coming from the air resistance. We tend to call this drag. Well, liquids can exert drag on a swimmer, or fluids can exert drag on an object falling through the air. So this drag force is like friction. It's a force that's going to oppose motion. A special case happens when somebody jumps out of an airplane and they start falling, and this air resistance builds and builds and builds and builds. If we let them fall for a long enough period of time, it is possible that that air resistance up against them will equal the weight force going down. When this happens, you know, of course, as you fall out of an airplane, you're going to fall faster and faster and faster. But eventually, you will fall the fastest speed that you can reach. This speed is called terminal velocity. Terminal velocity happens when the weight force down and the friction force up are equal to each other. Then you're traveling at terminal velocity. We could change the terminal velocity by changing your surface area, by changing how much space you take up. So you might see people that jump off those cliffs and they wear kind of winged parachute suits, or you might use a parachute and catch more air. This would allow us to change the terminal velocity that we fall at. Certainly we would want to do that if you were jumping out of a plane, because we would like our terminal velocity to be a safe landing speed instead of not so safe.